Imagine standing at the edge of the world. Not metaphorically, literally at the boundary of the last great wilderness on Earth, where wind screams at 200 kilometers per hour, where exposed skin freezes in under a minute, where the silence between gusts feels ancient and absolute. Beneath your feet lies not rock, but ice. Kilometers of it. Ice so old it contains air bubbles from a world that existed before human civilization, before the first cities rose from the mud of Mesopotamia. You are standing on the largest repository of frozen freshwater on the planet, and it is melting. Not slowly, not in some distant geological sense we can afford to observe from a comfortable remove. It is melting now, in real time, in ways that are rewriting the models scientists built only a decade ago. The ice sheet of Antarctica holds enough water to raise global sea levels by nearly 60 meters if it were to melt entirely. That is not a prediction. That is a measurement, a cold mathematical fact carved into the physics of water and gravity. The question that keeps glaciologists awake at night is not whether the ice is retreating. It is whether we have already crossed thresholds that cannot be uncrossed, whether the collapse we are witnessing in slow motion will become, within centuries or perhaps decades, something catastrophic and irreversible. To understand what is at stake, you have to understand what Antarctica actually is. Not as a place most people will ever visit, but as a planetary system. The continent sits at the bottom of the Earth like a giant thermostat, a white mirror reflecting solar radiation back into space, a cold engine that drives ocean circulation patterns responsible for distributing heat, nutrients, and weather across every corner of the globe. Antarctica is not isolated. It is deeply, invisibly connected to the climate of New York, Mumbai, Lagos, and Shanghai. When it changes, the world changes with it. The Antarctic ice sheet is divided into two major sections. The East Antarctic ice sheet is vast and relatively stable, sitting atop bedrock mostly above sea level. The West Antarctic ice sheet is smaller, but infinitely more dangerous. It rests on bedrock that in many places lies hundreds of meters below sea level, a configuration scientists describe as marine-based. That distinction matters enormously. Ice sheets resting below sea level are fundamentally unstable in ways that ice on high ground is not. They are vulnerable from the bottom up. And that vulnerability is exactly what warm ocean water is now beginning to exploit. For most of recorded history, the ice shelves fringing Antarctica, vast floating platforms of ice extending outward from land-based glaciers, acted as buttresses, holding back the inland ice the way a door wedge holds back a heavy door. The Southern Ocean surrounding the continent, while cold by human standards, is not uniform. Deep beneath the surface, hundreds of meters down, there exist layers of relatively warm water that originated in the subtropics and traveled through complex oceanic pathways to arrive beneath the Antarctic ice shelves. For decades, the cold surface waters of the Southern Ocean acted as a lid, keeping this warmer water away from the ice. That lid is weakening. As global temperatures rise, changes in wind patterns around Antarctica, driven by the ozone hole and greenhouse gas accumulation, are altering the upwelling of deep ocean water. Warmer water is being pushed closer to the ice shelves, intruding beneath them, eating at them from the underside in a process almost entirely invisible from above. There are no dramatic calving events to film, no thunderous crashes of ice into the sea. Just a quiet, relentless dissolution at the grounding line, the point where the glacier's base lifts off the bedrock and begins to float. As this grounding line retreats inland, the glacier behind it loses its anchor, its restraint. It begins to accelerate. Scientists drill through hundreds of meters of ice to deploy sensors into the frigid water below. Satellites measure millimeter-scale changes in ice surface elevation from orbit. What these instruments are telling us is deeply unsettling. At the heart of this crisis, dominating every conversation in glaciology for 2 decades, is a single glacier so consequential it has been given a name that captures both its significance and its terrible potential: Thwaites Glacier. In scientific circles, it is sometimes called the Doomsday Glacier, a name that scientists apply with reluctance, knowing the weight it carries, but unable to argue seriously against its accuracy. Thwaites is roughly the size of Florida. It drains a vast portion of the West Antarctic ice sheet, funneling ice from the interior of the continent into the Amundsen Sea. On its own, Thwaites contains enough ice to raise global sea levels by approximately 65 centimeters. But its true danger is not what it holds directly. It is what it is holding back. Thwaites acts as a cork in a bottle. Behind it, its presence slows and constrains the flow of neighboring glaciers across a drainage basin of staggering scale. Were Thwaites to collapse, and scientists are increasingly concerned that destabilization may already be underway, it would remove the restraint currently holding back a volume of ice sufficient to raise global sea levels by more than 3 meters. Not in an afternoon, not in a year, but potentially within centuries. And in the context of civilizations built on coastlines, stable for millennia, centuries is not a long time. The mechanism scientists fear most is called marine ice sheet instability, a process first theorized in the 1970s but treated for years as theoretical rather than imminent. The principle is stark in its simplicity. When a glacier's grounding line sits on bedrock that slopes downward as you move inland, which is the case over much of the West Antarctic basin, any retreat of that grounding line exposes deeper, thicker ice to the ocean. Thicker ice floats higher, creating a taller cliff face subject to greater stresses and more rapid calving. The retreat becomes self-sustaining. The deeper the grounding line retreats, the faster it retreats. There is no natural break in the geology beyond a critical threshold. This is not a computer model generating frightening projections. This is physics. Satellite observations have confirmed that Thwaites' grounding line has been retreating.
Direct exposure.
The glacier has lost contact with a stabilizing underwater ridge that previously slowed its flow. The ice shelf extending in front of it, already weakened, already fractured, is developing a network of cracks that scientists describe, with the precision of clinicians delivering a difficult diagnosis, as suggesting the shelf may break apart within years or a decade. When that happens, the glacier's exposed face will be a cliff of ice rising tens of meters above the waterline and dropping hundreds below. A companion process, marine ice cliff instability, suggests such cliffs collapse under their own weight, calving enormous icebergs faster than the glacier can sustain, accelerating the loss in a cascade that feeds on itself. This domino effect is not a metaphor. It is the literal mechanical reality of how interconnected ice systems behave. When one ice shelf disintegrates, it removes the back pressure on the glaciers flowing into it. Those glaciers accelerate. Their increased flow introduces more ice into the ocean faster. Adjacent ice shelves, undermined by warmer and fresher water, become destabilized in turn. The process propagates. It does not stop at the boundaries drawn on scientific maps. The West Antarctic ice sheet is a system, and systems once perturbed beyond a threshold find new equilibrium states that look nothing like what preceded them. We have already watched a version of this happen. In 2002, the Larsen B ice shelf, a platform of ice roughly the size of Rhode Island that had existed for at least 10,000 years, collapsed in a matter of weeks. Scientists watching the satellite imagery were stunned. The speed was unlike anything their models had predicted. Within months, glaciers that had flowed slowly and steadily into Larsen B for centuries were accelerating at rates 8 times faster than before the shelf disappeared. The restraint was gone. The ice that had been buttressed was now free. And in this context, freedom is a catastrophe. Larsen B was not an anomaly. It was a preview. The consequences of what is unfolding in Antarctica are not abstractions. They are engineering problems, displacement crises, and geopolitical realities the world is already beginning to confront. Sea level rise is not uniform across the planet, a counterintuitive fact that surprises many people encountering it for the first time. The gravitational field of an ice sheet actually pulls ocean water toward it. When that sheet loses mass, its gravitational attraction weakens, and the water it was drawing toward itself redistributes across the global ocean. Regions far from Antarctica, the coastlines of North America, Europe, and Asia, may experience sea level rise faster than regions closer to the ice. The places that feel most distant from the frozen south are, by the arithmetic of gravity and fluid dynamics, among the most exposed. Consider what a single meter of sea level rise means for the world's coastlines. Miami already floods during king tides unrelated to storms, a phenomenon locals call sunny day flooding. Bangladesh, a country of over 170 million people sitting on a vast river delta barely above the Bay of Bengal, faces losing enormous portions of its most productive land. Jakarta was sinking so rapidly from groundwater over-extraction that the government made the extraordinary decision to relocate the national capital entirely. Shanghai, Ho Chi Minh City, Alexandria, Lagos, Dhaka, New Orleans, Rotterdam. The list of cities facing severe exposure to rising seas reads like a catalog of human civilization's greatest coastal achievements. The World Bank has projected that without adaptation, sea level rise could create over 200 million climate migrants by 2050. Entire island nations face the genuine prospect of becoming uninhabitable within the lifetimes of children already born.
Sloping basin, rapid retreat risk, system remains unstable.
What makes the Antarctic situation particularly difficult is the uncertainty that remains. The most extreme scenarios could mean meters of sea level rise within centuries. The more moderate scenarios suggest tens of centimeters by century's end. The difference between them is the difference between expensive adaptation and civilizational disruption. That uncertainty is not a reason for inaction. It is a reason for urgency. The scientific community has responded with remarkable coordination. The International Thwaites Glacier Collaboration brought together hundreds of scientists from multiple nations to study the glacier in unprecedented detail. Autonomous underwater vehicles mapped the cavities beneath the ice shelf. New satellite missions measured changes invisible to the naked eye. Their findings confirmed the fears. Warm water intrusions are more extensive than previously understood. The timeline for potential destabilization may be measured in decades, not centuries. Standing at the edge of this frozen world, the mind struggles to hold simultaneously the extraordinary beauty of what is there and the extraordinary significance of what its loss would mean. The ice does not look fragile. It looks permanent, implacable, geological. But permanence is a story we tell ourselves about things that have not yet changed within the span of a human life. The ice was here before our civilizations. Our civilizations assumed it would always be here. That assumption is one of the most consequential we have ever made. The frozen continent is sending a signal written in retreating grounding lines and accelerating glaciers, in fracturing ice shelves and warming ocean water, in the data transmitted by instruments deployed at the edge of what is survivable. The signal is not ambiguous. The ice is changing. The question that will define coastal cities, island nations, and hundreds of millions of lives in the decades and centuries ahead is whether the world that created this problem will find the will, the technology, and the coordination to slow it before the most critical thresholds are crossed. Antarctica does not wait for our answer. It is already moving. Thank you for watching our video, GeoFuture, the channel that shows the future of our planet.